तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to the lecture series on the topic of engineering chemistry. This is a series of lectures being given to undergraduate science and engineering students in the country and elsewhere, and is part of the National Program on Technology Enhanced Learning, a project funded by the Ministry of Human Resource Development, Government of India. I have been giving the series of lectures on the first module on engineering chemistry, the module being the atoms and molecules, and on the fundamental atomic structure principles and principles of quantum chemistry, which we hope that all engineering students should be familiar with. My name is Mangala Sundar. I am from the Department of Chemistry, IIT Madras, Chennai, and the email is mangal@iitm.ac.in. In today's lecture, we will continue with the hydrogen atom that we started in the last lecture, namely lecture number 5. I introduced the spherical polar coordinate system for the study of hydrogen atom, stating that this coordinate system enables us to solve the Schrodinger equation for the hydrogen atom rather in a straightforward manner by affiliating the mathematics with mathematical equations that have been known for quite some time. The Schrodinger equation for the hydrogen atom is also the first real contact with systems of atomic nature, and in which the full mathematical machinery can be employed to show analytic solutions. We will not solve the problem here, we will state the problem and we will state the solutions, as has been the tone of this series of lectures. This is an introductory lecture, or this course is an introductory course. The solutions for the mathematical equations that enter in hydrogen atom are a bit more detailed than the mathematics that you are already familiar with. The differential equations that come into the picture require solutions using slightly more advanced methods, which I hope as engineering or science students pursuing your higher degree, you will see them in later years, particularly in special function techniques, orthogonal polynomials. These are all mathematical methods in the solutions of differential equations. We will only state the solutions, but more importantly we will try and understand what is the pattern in all these solutions and how we can make sense out of these solutions in terms of the orbital picture that you are familiar with from your preliminary or the previous encounter that you had with the hydrogen atom. Okay. So in today's lecture, which is lecture number 6 on atoms and molecules, which is part of the model problems in quantum chemistry, we will continue to look at the hydrogen atom, and in this lecture we are only going to look at two things. One is the separation of the wave equation expressed in spherical polar coordinates, or theta and phi, or theta and phi. The second part is the radial solution today. We will not look at the angular solution, we will not have the time to do the angular solutions. but we shall examine the radial solutions and make sense out of the results. Okay. So, the radial equation, the Hamiltonian for the hydrogen atom, if you recall from the previous lecture, the kinetic energy was written as minus h bar square by 2 m e, the mass of the electron, the x component of the momentum dou by dou x minus I h bar dou by dou x, the y components and the z components. This is the whole of this is the kinetic energy. And a potential energy term which is E square, that is of course a charge of the nucleus Z, but that is equal to 1 in this case by 4 pi epsilon naught r, where r is the radial distance of the electron as a dot from the nucleus with a classical model, classical picture expressed in quantum mechanics, quantum mechanical representation, because we have written the momentum in the form of the derivatives. Okay. Now, this was converted into the r theta phi coordinate system in the last lecture, and I would like to rewrite or write the Hamiltonian using the radial coordinate system, radial or the polar coordinate system as minus h bar square by 2 m e, okay, 1 by r square dou by dou r square dou by dou r, then there is the theta phi terms plus 1 by r square sin theta dou by dou theta sin theta dou by dou theta plus 1 by r square sin square theta dou square by dou phi square. This is the polar coordinate representation of this term. This one, the kinetic energy term that you have. Okay. In the r theta phi representation. So, and then of course what we are left with is, this is the kinetic energy term, what we are left with is the potential energy term, which is minus z e square by 4 pi epsilon naught r, and you know r is equal to square root of x square plus y square plus z square. Okay. Now, when we say that the purpose of going into the polar coordinate system is to simplify the Schrodinger equation and separate it. Okay. The form that I just wrote down does not look like any simpler than the form that you have in Cartesian coordinate system. Actually, the kinetic energy part is extremely simple looking in the Cartesian coordinate system. What causes the problem is, in that representation, is r, which is square root of x square plus y square plus z square. So, even though the kinetic energy form and the potential energy form are simple looking, they are not separable in the way they are written in the Cartesian coordinates. What do we mean by this? You have to go back and recall the particle in a 2D box. Where we employed a wave function psi x of y as a product of one coordinate only, the x function, and a product of the y coordinate only, and we were able to write the equation h bar square by 2m dou square by dou x square plus dou square by dou y square acting on psi, giving E psi for the particle in a 2D box, free particle, and bounded by V is equal to infinity at the edges. Okay. This was separable when we assumed the wave function to be of this form. The equation separated into two one-dimensional equations involving an x only, giving you an energy component Ex in terms of h square by 8 pi 8 m L square n1 square, and likewise for n2 square for Ey, and then the total energy was of course the sum of these two terms 8 m L square n1 square plus n2 square. But the nice thing is that the representation of this wave equation could be simplified into two one-dimensional wave equations by the proposition that the wave function psi is a product of two wave functions, each of which depends only on one coordinate. Okay. This is you recall that this was called the method of separation of variables in that lecture. Now, even though the hydrogen atom equation that you have here, the Hamiltonian that you have here, looks far more complicated in terms of the derivatives appearing in all places like this. The nice thing about this representation is that this can be separated into an R dependent equation only, a theta dependent equation only, and a phi dependent equation only. It may not be obvious, but we will go through that part rather elaborately to show that the equation is in fact separable. Convince yourself through the mathematics in the next 10-15 minutes that it can be easily separated. And by simply following this lecture, of course you will not understand this. You will have to do this on your own after some time, write this equation and go through the mathematics exactly the same way and practice it. But once having separated this, I will not give you the method of solving each one of these equations, but will give you only the solutions. So let us try and separate these equations one step at a time. Okay. So the first thing is, let's multiply the Schrodinger equation by R square by R square. Let's write the overall wave function, step 1, 2. The overall wave function psi or theta phi, let us for the time being write this as a radial function only and a function which depends on theta and phi. We will not separate this now, we will do it later, but we will write this as product of a radial function or a function R which depends only on the radial coordinate and a function which depends on theta and phi, and substitute this in h psi is equal to E psi. Okay. So let us write the equation. When you multiply this by R, what you have is minus h bar square by 2me, 1 by R square is gone, you have dou by dou R square dou by dou R acting on radial function R of R y theta phi. Okay. Now it is quite clear that the radial derivative will act only on the radial function, and with respect to this function this is of course the total derivative. So we might as well write this in a slightly different way by taking into account the full derivative and keeping all the other things outside, namely d by dr R square dr by dr, because that is the radial part, and this whole thing is multiplied by y theta phi. This is the first term. Now if you do the same thing for the next term, what you have is minus h bar square by 2me. Since we have multiplied by r square, we have only 1 by sin theta. Okay. Now this is a dou by dou theta. Since the function y is a function of both theta and phi, we will write this as a partial derivative dou y by dou theta, meaning that the phi part will be kept constant. And of course this will be multiplied by the radial part, which is a multiple. And likewise for the other angular part, minus h bar square by 2m e, mass of the electron, 1 by sin square theta dou square y by dou phi square, and of course this is also multiplied by radial part. This is all of the kinetic energy acting on the wave function, minus z e square by 4 pi epsilon naught multiplied by the radial part and the angular part y theta phi. I would write this as one term. Okay. This is the h psi is equal to, now e psi, since we multiplied everything by r square, there is an r missing here, but we are multiplying this by r square, so we will have to write the r here, z e square r by 4 pi epsilon naught, and this becomes e r square r of r y of theta phi. Okay. Now given this form, you can see this in full screen, that if we divide the whole equation by this r of r y of theta phi, let me just mark this, let us divide the whole equation by that, then what you will see is this y will go away and there will be a 1 by r here, because you see this is dr by dr, this is not this is an operator, so you have to divide 1 by r here, and you will have a 1 by y here, you will have a 1 by y here. Let us write that down. Okay. So divide the above equation by r of r and y of theta phi. So when you do that, it is minus h bar square by 2me 1 by r d by dr r square dr by dr, and let me bring the other r dependent terms here, namely minus z e square r by 4 pi epsilon naught. Okay. There is no factor here, and then there is one more, which was the energy term on the right hand side, which if you have to bring it on this side, it is minus e r square. All of this depend only on r, and the leftover terms are minus h bar square by 2me 1 by sin theta dou by dou theta sin theta dou y by dou theta. Of course there is a y in the denominator when we divide the whole thing by r and y, and then there is one more term which is minus h bar square by 2me y 1 by sin square theta dou square by dou phi square of y, and that is it. The whole thing is equal to 0 as we brought the e on this side already. Okay. So now you have an equation which, if you look at it carefully, has a term which depends only on the r and has two terms which depend only on theta and phi, and remember that r, theta, phi are independent coordinates. Therefore you see that this equation has separated the terms according to r dependent terms only and theta phi dependent terms only. And therefore, if you write this as something like a quantity which depends only on a function of r and another which is a function of theta and phi, if I do this symbolically, is equal to 0, and this is valid for all values of r and all values of theta and phi, which is in the hydrogen atom case, r goes from 0 to infinity, theta goes from 0 to pi, and phi goes from 0 to 2 pi. If it is true, then the only possibility for this equation to be solved consistently is that this whole thing is equal to a constant and this whole thing is equal to the negative of the constant, so that beta minus beta is equal to 0. Okay. So now you see what is meant by the separation of the variables in the case of the hydrogen atom when you express the kinetic energy in a rather complicated form using the r theta phi coordinates, which wasn't there if you were to write this using the x, y, z coordinate system. Okay, it's not over yet. We have only separated r and theta phi. Now we can do further by writing the theta phi equation and trying to separate this into a function which depends only on theta and a function which depends only on phi or phi. Let's do that. Okay. So let's keep in mind that we call this whole theta dependent quantity as equal to minus beta. Okay. So let's write the theta phi equation. The theta phi equation is minus h bar square by 2me times y dou by dou theta, sorry, that is 1 by sine theta is there, so let's write this carefully. One by sine theta dou by dou theta on sine theta dou y by dou theta. Okay. This is the first term of the theta phi equation, and then you have minus h bar square by 2me times y 1 by sine square theta dou square y by dou phi square is equal to minus beta. That is what we set this equal to. A function of theta phi is equal to minus beta. Now if we have y theta phi expressed in the same way as we did earlier, namely write this as a function of theta only and a function of phi only, then this equation can be separated further into two equations, one dependent on theta and one dependent on phi. Then the separation of the three dimensional r theta phi problem of the hydrogen atom into three one dimensional problems, each of which depends only on one coordinate, is complete. And afterwards, of course, you have to think about solving such equations. Fortunately, there are methods that physicists found out knew earlier, and those methods could be applied directly here. Okay. Let's just do the separation on the theta and phi. So if you substitute, again you have to do the same thing, you substitute and then you divide by theta and phi on both sides. So let's write this equation with that having done. Substitute, divide by theta of theta and phi of phi. Okay. Let's do that. So what you get is minus h bar square by 2me. You will get a theta in the denominator, and within brackets you will get 1 by sine theta d by d theta sine theta d theta only by d theta. This is the first term, and the next term will be minus h bar square by 2me times phi, and you have 1 by sine square theta d square by d phi square of capital phi is equal to minus beta. But then it is obvious from this equation that if we multiply this by sine square theta throughout, okay, let us do that. we multiply this by sin square theta, what we get is sin theta here, and what we get here is that this goes away. Okay. Let me erase this also and then put the two together. Okay. This is that, and what you get here is minus beta sin square theta. Okay. So now you see that this is easily separated into a theta dependent term only by clubbing these two together, this one and this one, as a function which depends only on theta, and then a function which depends only on phi, and then you have the same thing, that a g1 of theta some function and a g2 of phi is equal to 0. Therefore, this is equal to a constant and this is equal to the negative of that constant. Okay. So then the three equations are completely separated. What is the result? Let us go and take a look at those equations in the slide here. Okay. So this is the same equation that I have written down with the minus h bar square by 2m e, the mass of the electron. The e subscript is not here, but you can add that, and this equation is something you have seen it already, and the r part that I have written down, of course the constant beta here, you must have a minus sign, but it does not matter, we will call this as the new constant beta. So the radial part is the minus h bar square by 2me has been sort of multiplied out here, and this beta contains that with some sign changes. So the beta that you have here can be associated with what I wrote down a few minutes ago by this term, that is you multiply with minus 2me by h bar square, the beta that I have written down, then this is the constant that is there in the slide. Okay. The point is that this is a solution for the radial coordinate, and later on we will learn that the solutions are given in terms of the orthogonal polynomials known as the log r polynomials. Likewise, the theta equation, 1 by sin theta d by d theta sin theta, this one, and the separation of this, when we did that we got this into two independent equations, but the solutions y, which contain both theta in blue and phi in green, these are two variables to show you y depends on both of them, this solution y is known as spherical harmonics in the mathematics that we deal with. Okay. Now the r solutions, let us now look at the radial functions. Radial functions, the radial equation, if you remember, contains a constant called beta, this one, it contains this constant. Okay. This constant is of course related to the theta equation, and the constant also appears in the theta equation. If we look at the theta phi equation solution, theta phi equation, look at the solution for the theta phi equation. Can be obtained analytically you remind yourself of this, can be obtained analytically here, this equation, this is the theta part and the phi part, together the sum of this is equal to 0. This can be obtained analytically if this beta has the special form, namely a number integer L into L plus 1, where L can have values 0, 1, 2, 3, etc. Okay. Integers only. This L, as a result of the solution of the theta phi equation, also controls the radial function because the L appears in the radial equation here. Okay. Therefore, the radial function depends on two quantum numbers, one that comes with the L from the Thetaf equation and one with the radial equation itself. Radial equation comes up with a quantum number requirement n which is 1, 2, 3 etc. and an L which is 0, 1, 2, 3 etc. But since the L is part of the radial equation coming from the theta phi, L cannot be arbitrary, but for any n, L has to have the value 0, 1, 2 etc. up to n minus 1 only for satisfactory solution of the problem, solutions psi in terms of the radial function and the angular function. This is part of the mathematics. There is no way I can take the time here and expand to this without spending another 1 or 2 hours, and that is not our purpose. Our purpose is that up to this point that we can understand the mathematics of separation. Let us now believe that the mathematics has been done by the mathematicians and the physicists. We have verified this, we know that this is correct, and what we have is the solution which is given by this requirement. The solutions are, the radial solutions contain two quantum numbers n and L. The values of n can be integers, there is no n equal to 0, it starts with 1, 2, 3 etc. and L is bounded by the requirement of the n, namely L is up to n minus 1, sorry, L should be 0 is also allowed here, so please insert a 0 in the slide. Okay, there is a 0 here that is missing. So n is equal to 1, the only solution is L equal to 0. If n is equal to 2, the quantum number L can have two values 0 and 1. For n equal to 3, the quantum numbers can be any one of the 3, 0, 1, 2 and so on. What are the radial solutions? Let us look at the radial solutions by the actual functional form obtained by solving the radial equation. Okay. The radial solutions contain two parts. They contain two parts, one which is exponential, namely e to the minus r by n a naught, where a naught is the Bohr radius. You can look for the expression for the Bohr radius a naught in terms of the constants that we have given, namely the h bar, the mass of the electron, the charge and things like that. So this whole thing comes out from the constants in the Hamiltonian. But the thing is, the exponential has now the arguments which are dimensionless, that is r by a naught being a radius itself of a constant radius, 0.53 angstroms if you want to know what it is, and the quantum number n is 1, 2, 3 etc. Okay. There is one part to the radial function. The other part is part of what is known as the Laguerre polynomials. Laguerre polynomials. Okay. The harmonic oscillator solution, if you recall in the previous lecture, also had two parts, a Gaussian function, an exponential of minus x squared, if you remember that. And then there was a function called the Hermite polynomial, which keeps changing, or it actually is a polynomial with increasing powers of x as we go down, as we increase the quantum number n equal to 1, 2, 3 etc. The same way here, the Laguerre polynomials are also polynomials of certain power, and the exponential is such that the whole wave function eventually vanishes when r becomes very large. You remember the boundary conditions are important in all the problems that we solve in quantum mechanics till now and also in the future. The boundary conditions in this particular case tells you that the wave function must vanish at the boundary. Where is the boundary? The boundary is at r equal to infinity. Okay. So the wave function must go to 0 at r equal to infinity. Nothing better than an exponential function, and in fact it comes out from the solutions that way, that it is e to the minus r by n a naught. Recall, if you have a function e to the minus r by some a naught, and if you have a polynomial of r by a naught again, okay, you have a polynomial again, you see, which is essentially r by a naught to the nth power being the leading term, where n is 1, 2, 3, etc. Remember that eventually e to the minus r by a naught makes this whole product vanish. The only thing is, as n increases, the value of r by a naught for which the exponential starts dominating over the polynomial, that value r by a naught becomes farther and farther, is higher and higher. For small values of n, the exponential drops off very quickly, but for very large values of n, the exponential does not dominate this whole product, and the wave function stays big or increases for much larger values, and then only it decreases. But for any finite power of n, the exponential eventually kills the wave function, giving you the right boundary condition that the hydrogen atom wave function, the radial part, vanishes. Well, whatever be the angular part, the angular parts are between theta and phi, they do not go to infinity, they are bounded, and therefore the overall wave function vanishes at the boundaries for a sphere of infinite radius, irrespective of what the values of the theta and phi coordinates. So the boundary condition is contained in the solution. Since we are not in a position to basically go through the algebra and verify ourselves that this is indeed the solution, let us try and understand what the solutions convey in meaning. They contain the right boundary conditions. One, the second part. For n equal to 1, there is only one radial solution. For n equal to 2, there are two radial solutions. Namely, corresponding to n equal to 2, l equal to 0, one set, and n equal to 2, l equal to 1, another set. Okay. And the successive cases, as you increase n to 3, 4 and 5, etc., the total number of solutions is n, corresponding to l equal to 0, 1, 2, 3, 4 up to n minus 1. So there are n solutions for any radial wave function with the principal quantum number n. The values of l, of course, are 0 to n minus 1. The other thing is, the radial and angular part also control the other phi part. The phi equation will introduce its own quantum number in the solution of the phi part, but that quantum number m will be limited by the n and the l, such that if n is 1, 2, 3, etc., and if l is 0, 1, 2, 3, etc., the phi part contains a quantum number m which goes from 0 plus minus 1 plus minus 2 up to l for any value of n. So this is the hierarchy of the quantum numbers in the case of hydrogen atom. Go back and look at the phi equation if you are doubtful. Okay, here is the phi part. Go back and look at the phi part here. You see the theta phi part contains the sine theta, beta sine square theta, all these things are the theta part, and then there is the phi part. So this whole equation on the theta part of it, if we set it equal to a constant, then this is set equal to the negative of the constant, so that the sum of these two is equal to 0. Therefore, the phi has a certain constant associated with that, and this equation, the phi equation, ultimately can be seen to be, the phi equation can be written as basically minus h bar square by 2me d square capital phi by d phi square plus a constant times phi is equal to 0. Such equations are known to have very simple equation. Let me write the constant as with the minus sign, this should also be minus, and this is minus k square. Let me write this in the form of a slightly simpler quantity in the form of, say, k prime square capital phi is equal to 0, and this equation also has the boundary condition. You remember, phi depends on the value phi, and the value of phi is between 0 and 2 pi. That is our spherical system. Therefore, any other value of phi, for example 4 pi, 6 pi, or anything greater than 2 pi, should be represented for what you call as the single valued and continuous function. The wave function phi part must satisfy small phi plus 2n pi, where n can be 0, plus minus 1, plus minus 2, etc. Therefore, this introduces a quantum number for the phi part m, which I had just written down here as 0, plus minus 1, plus minus 2, etc. up to L. So, given all this hierarchy of equations and the results, now let me look at the radial part first, then we will look at the angular part, and then we will go to the angular part with the phi part. The radial solution for n equal to 1 and L equal to 0 has, of course, the charge and the a naught, the Bohr radius, to the power 3 by 2. This is a normalization constant which makes the wave function psi star psi d tau integral to unity. Okay. But the wave function is e to the minus z, which is the nuclear charge, times r by a naught, and the n is equal to 1 here. It is r by n a naught is the general form for the exponential equation. For n equal to 2, there are two solutions, L equal to 0 and L equal to 1. Let us look at the L equal to 0 case. The L equal to 0 case has an exponential of minus zr by 2 a naught. The n appears here, and it has a simple function 1 minus r by a naught z by 2. Okay. So, this is a monomial, that is, it is a function to the power rth power 1. The other one is also n equal to 2, L equal to 1 is also zr by a naught e to the minus zr by 2 a naught. But the point is, this function is 0 at r equal to 0, and it never goes to 0 for any value of r other than r equal to infinity. This one, on the other hand, n equal to 2, L equal to 0, which contains 1 minus zr by 2 a naught e to the minus, does not go to 0 at r equal to 0. In fact, at r equal to 0, it is simply this constant, this exponential is 1, this is simply 1, but it does go to 0 when r is equal to 2 a naught by z. Okay, z is charge, therefore, when r is equal to 2 a naught, this function goes to 0. Therefore, it has a radial node at an intermediate value. The radial node is there for the function L equal to 0, n equal to 2, is not there for the function L equal to 1, n equal to 2. What about n equal to 3? You see that the pattern of the log polynomials and the exponential is such that the exponential is e to the minus r by 3 a naught. For n equal to 3, L equal to 0, you have that. For n equal to 3, L equal to 1, you have that again, and for n equal to 3, L equal to 2, you have that again, zr by 3 a naught. but looking reversible, I mean looking back from this side, you see that L equal to 2 contains an R square which goes to 0 at R equal to 0, but never anywhere else other than infinity. N equal to 3, L equal to 1, if you look at it, it does go to 0 at R equal to 0, R equal to infinity, and also 1 or in between where this particular function 1 minus ZR by 6 A naught is 0. Therefore, this has one radial node for L equal to 1. The function for the N equal to 3, L equal to 0 is a quadratic function multiplying an exponential which does not go to 0 at R equal to 0, but it goes to 0 in two other places in between, and then of course at R equal to infinity. So this function has two radial nodes corresponding to the two roots of this quadratic equation. Okay. So the pattern should be clear now immediately. What is it for N equal to 4, for example? For N equal to 4 and L maximum 3, you must have a term something like R cube e to the minus ZR by 4 A naught. N, this N is always the principal quantum number associated with that. For L equal to 2 in N equal to 4, you will have a function R and an equation something like R minus R by A naught minus some constant times e to the minus ZR by 4 A naught. That is, it will have one radial node. For N equal to 4, L equal to 1, you will have, when you do the mathematics and expand the log-R polynomials rightly, it is R square times a quadratic in R multiplied by e to the minus ZR by 4 A naught, two radial nodes. For N equal to 4, L equal to 1, L equal to 0, it is, sorry, I must have had this as R square and I must have this as R. Please make a change here. R cube, R square, R. And for N equal to 4, L equal to 0, you have a cubic in R e to the minus ZR by 4 A naught, and this has three radial nodes. This function is 0 at R equal to 0. This is not. L equal to 2 is 0 at R equal to 0. L equal to 3 is also 0 at R equal to 0. And of course, all of this go to 0 at R equal to infinity. So you have the number of radial nodes which you can immediately see for these functions, the number of radial nodes other than 0 if it is applicable, okay, other than 0. Of course, you see it does not exist for the L equal to 0 case and infinity, other than 0 and infinity. It is not a node because it is just where the function goes to 0 forever. And what you have is N minus L minus 1. This is the number of radial nodes that you have. So when you have a function with L equal to 0 quantum number, you have the maximum number of radial nodes corresponding to the L value maximum. If L is 3 and N is, sorry, if N minus 1, if N is 4 and L is 0, it is 3 radial nodes. If N is 4 and L is 2, 1 radial node, and so on. So the pattern of these functions should be recognized. If we are unable to solve this equation using simple mathematics, we must understand what the functions are and how do they behave for different choices and recognize the pattern from them. Now it is easier if we recognize this using a graphical representation of the same thing. So let us quickly do that before the time runs out on us. Okay. Yeah. Before I do the graphical representation, I would also want to point out this, namely the energies for the hydrogen atom, that is the E that you calculate, which is there part of the radial equation. You remember that the H psi is equal to E psi, that E got associated with the radial equation and not with the angular equation. The energy E turns out to be exactly the same expression as what Niels Bohr calculated using his ad hoc approximate, or the method that with the approximation that the angular momentum is quantized or the energies have 1 by n square form. The quantum number, of course, in this particular case arises naturally by assuming that the wave function, the Schrodinger equation, is correct. The arbitrariness here is that we do not understand why the Schrodinger equation is correct, but if we understand that, or if we accept that it is correct, then the rest of the solutions are naturally applicable and are derived from rigorous mathematics. Obviously this means that we are replacing the hypothesis of Bohr by the hypothesis that the Schrodinger equation itself is valid. But unlike that of the Bohr hypothesis, the Schrodinger equation is found to be working for all atoms, not just hydrogen atoms, and the electrons in the hydrogen atom, according to the Schrodinger equation, is described by 3 quantum numbers and 3 only. This is a non-relativistic Schrodinger equation. The 3 quantum numbers are the n, l and the m, which I haven't talked about. I will do that in the next lecture. Today we are concentrating on the n and l. Okay. I would in passing make a remark which is very important in recognizing the fundamental contributions of Paul Adrien Maurice Dirac, the English physicist. Is the father of quantum mechanics and introduced clear and concise mathematical ideas in quantum mechanics. He also generalized the Schrodinger equation to the relativistic motion of the electron and derived the spin quantum number as the 4th quantum number through his formalism, for which he eventually shared the Nobel Prize in 1933. Okay. His book, of course, is one of the most well known and probably the most mathematical rigorous book on the principles of quantum mechanics. It is still a classic book. However, I think reading this in the beginning of your quantum mechanics course can pretty much be a nail biter. I would say read quantum mechanics through simpler books, get yourself familiar with 2 or 3 such courses, and eventually go back and read Dirac's book. It tells you everything. Let us just quickly look at the plots of the radial function, namely the exponential minus r by a naught in this case. How does it look like for the radial n equal to 1 and the l equal to 0 case? The radial part, if I plot this as a function of r, you see it is a straightforward exponential. There is nothing, and as r by a naught goes to something like 5 or 6, that this wave function goes to 0. Let me go back to the next one. N equal to 2, l equal to 0. The radial function is 1 minus r by 2a naught, z is 1, e to the minus r by 2a naught. Now as you increase from r equal to 0 to higher values, you see this function becomes smaller, but this function is not 0. It goes to 0 at r equal to 2a naught, and then it is negative. For all values of r greater than or equal to 2a naught, it is negative. It goes down to 0 from a maximum to or equal to 2a naught, and then of course it stays negative, it keeps increasing, but the point is the exponential minus zr by 2a naught will eventually reduce it to 0, bring it to 0. Therefore this function has the radial node at this point or equal to 2a naught. Okay. N equal to 2, L equal to 1 is simply r times e to the minus zr by 2a naught. This starts from 0, increases as r increases, but this eventually tapers off the function, and so what you have is you see starting from 0, it grows from 0 to a maximum value, and then it goes back to 0 as r increases. This is the radial function for n equal to 2, L equal to 1. N equal to 3, L equal to 0 is a quadratic exponential minus zr by 3a naught. If you plot this, this quadratic has 2 roots, so the first root and the second root are such that the function is negative between the first and second roots. Let us just write this quickly. The function can be written for n equal to 3 and L equal to 0 as a function r minus a1 times r minus a2 times e to the minus zr by 3a naught, where these are the roots of the quadratic, and if we assume that a1 is less than a2, and if this is the radial function r, you see that the radial function is, when r is less than a1 and a2, from 0 to a1 this function is positive, between a1 and a2 this function is negative, and at a2 this function is 0, and when r is greater than a2 this function keeps on increasing as square r square, this function keeps on increasing as r square, but eventually the exponential goes down and this function goes to 0. Therefore what you have is, you have a positive part, a negative part, and then a positive part. N equal to 3, L equal to 0. It starts from a value, non-zero value, goes to 0 at a1, increases but then decreases at a2, it becomes 0, and then it keeps on increasing as r square, but the exponential eventually kills it off. So these are the two radial nodes for the quadratic function that you have here, and it is quite clear that when you do this for n equal to 3, L equal to 1, that you will have one radial node, namely it starts from 0, increases up to a certain value, then this function eventually for this value of r equal to 6a0 by z, this whole thing goes to 0. So you have one radial node, and then this function is negative, goes back to infinity, 0 at infinite r. And the last one is n equal to 3, L equal to 2, is r square times e to the minus z r by a0. You see where the maxima occurs, the maxima keeps on shifting because it is now r square, and the function grows much more before it is killed by the exponential minus z r by 3a0. So you have no radial node for this, but it starts from 0. You can see these together. In the case of n equal to 2, you see the radial function for the L equal to 0 and the L equal to 1 case together, and likewise you can see the 3 together, namely n equal to 3, L equal to 0, 1, 2, all three of them. The 0 is the one that starts from non-zero value at r equal to 0, the rest of them are both from this value 0, and you see there is one radial node in this pink colored or whatever, this colored function, whereas the green color shows you that there is no radial node, that is L equal to 2, this is L equal to 1, and this is L equal to 0. These are the radial functions that we have. Okay. Now the angular part we haven't done yet. In the next lecture we will continue this with the angular part. The angular part now contains two quantum numbers L and M, and the wave function, for completeness let me write in this lecture before closing it, the wave function psi depends on three quantum numbers n, L and M, and is written by the two quantum numbers r, n, L corresponding to 1, 0, all these things, and the angular quantum numbers y, L, M, theta and phi. Okay. This is the complete solution. The radial parts we have described today, the angular parts we will describe in the next lecture, along with the pictorial representations for the real parts of the angular distribution and the angular wave functions, and these are the shapes that you normally see for the s orbitals, p orbitals, d orbitals, etc. With that we will sort of understand qualitatively why the Schrodinger equation hydrogen atom has the solutions that it has, and how it could be obtained from the polar representation, the spherical polar representation of the Schrodinger equation Hamiltonian. And then we will move on to doing simple calculations using these in order to understand a little bit globally the mathematics associated with the hydrogen atom. It is very important for chemists and people who understand chemistry or who require chemical understanding at a slightly higher level to see that the angular shapes and the radial shapes come from exact solutions to the Schrodinger equation for the hydrogen atom. We will continue this with the angular part in the next lecture. Until then, thank you very much.